have collected some idea regarding the coordinate system, gamma function, and the distribution of a property and how this property from this distribution could be done average in lecture 4, 5 and 6. Now it is our time to formulate the Maxwell's distribution of molecular speeds. And in 1900, in James Clerk Maxwell, in 1859, James Clerk Maxwell first formulated this sort of very important distribution law, and the distribution law is totally based on probabilistic idea. On the concept of a probability, Maxwell's formulated this distribution law. And the distribution law, if I could write the distribution law first before going to formulation, then Maxwell Maxwell distribution law is that dnc by n equal to 4 pi divided by m by 2 pi kt and to the power 3 by 2 and e to the power minus mc square by twice kt and c square dc. And this left hand side DNC is the number of molecules in a gaseous system. The gaseous system have been taken as idealized system, having no interaction among themselves, and the container in which this gas remains is in stationary state, and this is also in thermodynamical equilibrium with these surroundings. So this DNC is the number of molecules of molecular mass m at a temperature T have the speed c to c plus dc, means having the speed c within the range dc. So where m is the total number of molecules present in this container. So naturally this one you can call, this is the favorable number of molecules which have this speed within this range, and this is the total number of molecules. So this ratio you can call the probability of a molecule to have the speed c within range dc, and this you can also say in an alternative fashion, dnc by n, it is the fraction of the molecules that have the speed c within the range dc at a temperature T, and m the molecular mass of this gas. So in both this way we can express this term dnc by n. D is given due to very small value of this number. The postulates. First we can say the postulate. postulates for the formulation of Maxwell distribution law. So there are 5 postulates. At least I have taken these 5 postulates which are important to derive the Maxwell's distribution law. And first postulate, the uniform distribution. Uniform distribution of this molecule. Uniform distribution of this molecule in this container. It means that the number density of this molecule at every point within the container will be the same. Means the distribution should be totally uniform. And the second one, the molecular motion. Molecular motion is completely random. Molecular motion is completely random. It means that the molecules can move in all directions with equal probability. And this one you can call isotropic property. Isotropic property of this molecular motion. The molecules can move in all directions with equal probability. They have no preference choice to move in a particular direction. Every directions are equally having the same chance for this molecule to move. And this is the isotropic property of this molecular motion. And number 3 is that the average, the resultant speed, this molecule could be the speed of this molecule can be resolved in 3 component velocities with respect to x, y and z. This is the x axis, and this is y axis, and this is z axis, and this is origin. Suppose u is the velocity of this molecule along this x axis, and v along this y axis, and w along this z axis. So u, v, w, they are the component velocities whose resultant speed is c. Resultant speed c. So this is if the resultant speed is c, its component velocities are, this is w, this is u, and this is v. And this resultant speed c square equal to u square plus v square plus w square. It is to be reminded that the resultant speed, it is a scalar quantity. It has only the magnitude and no directions. In all directions it can move. But u, v, w, they are the velocities. They are having the magnitude and also a particular direction vector quantity. So u, v, w are the velocities, and c is the resultant speed. C can be connected with this u, v, w in this manner. And these component velocities u, v, w are equally likely, means a molecule can move in x-axis, y-axis, z-axis without any preference. Not only that, these UVW, the component velocities, are mutually exclusive. Mutually exclusive means whenever the molecule is moving along this x-axis with a velocity u, this v and w equal to 0. Again, whenever this molecule is moving along this z-axis with a velocity v, u and w are 0. And similarly for this case of this z-axis. So they are equally likely and mutually exclusive, so that concept of probability we could apply. Not only that, Maxwell himself assumed that UVW, they are independent to each other. And now we are coming, this is fourth postulate, and fourth postulate is, though I have already told in my previous lectures that in kinetic theory of this gas, molecules are in random motions. Molecules are moving in all directions with equal probability in a variety of speeds. It means that whenever they are moving random, the molecules suffer two types of collisions. One is wall collision and other is intermolecular collisions. In case of wall collisions, the velocity is not changed, or speed is not changed. The speed remains the same. But in case of intermolecular collisions, the speed of these molecules are changing. And you know, or we could show in our future lectures, that in a second 1 cc gas, actually there are 10 to the power 28 or 27 around number of intermolecular collisions. So intermolecular collisions per cc per second is an astronomical figure. So the speeds or velocities of the molecules are also changing in this number. So you could not identify, you could not locate, you could not give any velocity to or any speed to any molecule at a particular time. It is constantly changing. It is constantly changing. Though at a given temperature, if the temperature have been kept fixed, then actually a definite fraction of the molecules, definite fraction, say dNCYN, have always a definite speed within a range. Means have speed, definite speed, have definite speed within small range, and this is called the steady state conditions. So this is actually the steady state condition. This is actually steady state conditions. Though the speeds or velocities are changing constantly, still then at a given temperature, a definite fraction of the molecules will always have a definite velocity or speed at a definite within a small range. And the fifth one, and the fifth postulates, this Maxwell distribution law is not applicable to the system, to the gaseous system, where some internal force field or external force field is operating. When internal force field means the intermolecular attractions. If the molecules have intermolecular attractions, say whenever the molecules are intermolecular attraction or repulsion, then this law is not applicable. This law is not valid. So for the real gas, Maxwell distribution law is not valid. It is valid only for this ideal gas in which there is no intermolecular attractions or repulsions. Say, if this molecule have the intermolecular attractions, then molecules in this bulk, number density of the molecules in this bulk is very high, where number density just near the wall is low. So uniform distribution is disturbed if the molecules are having the intermolecular or molecular interactions. And similarly, some external force field, say gravitational. Gravitational force. If the gravitational force is operating for this system, then suppose here due to gravitational force is operating. So this number density of the molecules is decreasing with the increase of height. So in this case, number density is less. In this case, number density of these molecules are high. So in this case also, uniform distribution is not present. So one thing is that the gaseous system is completely random, and the probability is always have a finite value. These are the two main aspects for deriving this Maxwell distribution law. Probability is always finite. Probability cannot be infinite. Probability could not be infinite. It will be probability actually less than or equal to 0 and greater than or less than equal to 1. This is the probability of this. Probability just as such, in all the cases, probability is having such range. Now we are going to formulate. Now we are going to formulate the Maxwell distribution law. Say molecules probability of a molecule to have x component velocity u within small range du. What will be the probability of a molecule probability of a molecule to have the x component velocity u within the small range du. Means suppose it is the x-axis, it is y-axis, and it is z-axis, and here it is 0, and this is u, and this is u plus du. Du is the range. This is the range. This is du. So what will be the probability? In this case, the probability Pu of a molecule to have the speed, have the velocity, x component velocity u, is equal to some function of u and this range. Here the range of this speed, velocity, greater will be the probability. If the range is increased, then Pu is also, probability is also increased. And not only that, range Pu having the some function of u, some mathematical expressions of this u, on which this probability will depend. I shall give one example. Say, in a class, there are some 100 students, and the students have their different amount of money in their pockets. If we try to guess out what will be the probability of a student to have the money 10 to 12 rupees, then it will be, this probability will depend on this range here 2, and also a function of u here 10. You certainly see, suppose what will be the probability of a student to have this money 100 to 102 money, 100 to 100 plus 2, then this probability will not be the same, though the range is same. So it is so this probability certainly depends on some function of u, here 10, 100, and suppose 1000 to 1002, probability will different. Here the probability say here f is the, so the probability will be different depending on 10, 100 and 1000. Which one will have the greater probability, that will be decided by the background of the students coming from. If the students are coming from this rich family, then this probability will be the higher than this one and this one. If the students are coming from this non so low economic region, then this one will be having the more probability than the others too. So, and again, if we do the range, suppose 10 to 4, here 100 to 104, here 1000 to 1004, range is double, then probability will also be double. Here suppose some student is having the money 13, then it is excluded. Here it is included. So more fraction of the students will have the money when the range is extended. what will be the function fu? What will be the mathematical expression of this function? Actually, suppose this is the x-axis, this is origin, this is x-axis, here it is u, here it is u plus du, here it is minus u, here it is minus u plus du. So molecule is having the same probability to move 0 to plus infinity, and here 0 to minus, same probability. So if the probability will be the shape, then expressions of this distribution function must not contain u, but it may contain u squared. And again, so it may contain u squared, not u. Again, whenever the u tends to infinity, then this fu tends to 0. So considering all other facets or aspects of the distribution function or the distribution x component velocity distribution function, it is to be the a into e to the power minus b u square. So here u, if u tends to infinity, then a fu tends to 0. A, B, these are the constants that depends on the nature of this gas molecules and the temperature. So it could be shown, but here for elementary idea we have decided the distribution function, x component velocity distribution function is a into e to the power minus b u square. A and b, these are the constants. So since the molecule have the same probability to move in any directions, x directions, y directions, z directions, so the format, format fv, format of this distribution function will be the same. Here also a into e to the power minus b u square, and fw will also have a into e to the power minus b w square. A, B, these are dependent on the nature of this gas and the temperature. So suppose, so if you then probability of a molecule to have EU, V, W simultaneously, and this will be probability PU into PV into PW, as the probability is a multiplicative property. So probability is a multiplicative property. So P U V W equal to d n U V W divided by n, fraction of the molecules, or probability of a molecule to have this velocity U V W within the range du, dv and dw. Here this range, here it is v, and here it is v plus dv, here it is w, and here w plus dw. dw is the range, dv is the range, du is the range. All the molecule is having the velocity u v w within the range du, dv, dw will be like this, and this is equal to fu and du into fv and dv into fw and dw. Now, so dn UVW divided by n equal to, we could write, instead of this one, we can write a to the power minus b u square and du into, instead of this one, a into the power minus b v square and dv into a to the power minus b w square and dw. This is the probability. This is the probability of a molecule to have the speed UVW, to have the velocity UVW within the range du, dv, dw. And this is equal to aq and e to the power minus b u square plus v square plus w square, and here the u, d, v and d w. We know that already. I have said this u square plus v square plus w square equal to c square. C is the resultant speed. So it could be right as aq e to the power minus bc square and the u, the v and the w. So this is in Cartesian coordinate. Velocity distribution of this molecule in Cartesian coordinate. We can express in polar coordinate. In polar coordinate, this polar coordinates, there are three coordinates, c, the resultant speed, and theta phi, azimuthal zenith angle and azimuthal angle. So we can write here d n c theta phi divided by n equal to aq into e to the power minus bc square, and instead of this c in polar coordinate, so this to be also expressed in polar coordinate, and you know the dx, dy, dz equal to r squared dr sine theta d theta and d phi. So in this case, in the case of velocities, du, dv, dw equal to, instead of radial distance, it will be c square dc and sine theta d theta and d phi. Theta is the zenith angle, phi is the azimuthal angle. So here it will be the c square dc and c square dc sine theta d theta d phi. Now if we like to consider the distribution of speed only irrespective of this direction, so theta and phi to be integrated in all possible ranges. So in this case, d n c by n equal to aq e to the power minus bc square and c square dc. Only we are considering this speed and not these directions, and here full range of theta is 0 to phi, and it is sine theta and d theta, and here it is d phi 0 to 2 pi. Azimuthal angle have this limit 0 to 2 pi. So in this DNC is the number of molecules having the speed c to c plus dc in all directions, and this is the fraction or the probability of a molecule. So this will be equal to a cube e to the power minus bc square and c square dc, and here it is minus cos theta and 0 to pi, and here pi and range 0 to 2 pi. So if we integrate and put this limit, then dnc by n is equal to a cube and e to the power minus bc square c dc, and this is 2 and this one is 2 pi. So the distribution function, dnc by n, distribution probability, it is the probability of a molecule to have these velocities, to have the speed c to c plus dc, or the fraction of the molecules have the speed c to c plus dc in all possible directions. So this will be equal to 4 pi and a cube e to the power minus bc square and here c square dc. Now our task is to evaluate the value of a. First, evaluation of a in terms of b. If we do integrate, actually this one you can write also this fc and dc. fc is the distribution function, speed distribution function, and dc the range. Speed distribution, it is the probability of a molecule to have the speed c within the range 1. When it is multiplied by dc, then range will be from c to c plus dc. So putting these normalization conditions, this is very popular in quantum mechanics. Normalization condition means all possible values of c, here fc and dc equal to 1. It means that 0 to all values of c, here dnc by n, instead of write this fc equal to this one, and this is equal to if you do this integration, then 4 pi a cube constant go outside of the integration, 0 to infinity, and e to the power minus bc square and c square dc. This one actually, this is the fraction of the molecules which are having all possible values of c from 0 to infinity. So this one equal to 1. So 1 equal to 4 pi a cube, and this could be done, this integration could be done very easily by using this gamma function. Gamma function, you know this integration 0 to infinity x to the power n e to the power minus bx square and dx equal to gamma n plus 1 by 2 divided by 2 into b to the power n plus 1 by 2, n by 2. So here n equal to 2. So it will be gamma 3 by 2 and divided by 2 b to the power 3 by 2. So these are the standard integrals, and these standard integrals could be done by means of gamma function very easily. So we are having 1 we are having the 4 pi a cube, 4 pi a cube into this one is half 1 by 2 b to the power 3 by 2 into gamma 3 by 2 means gamma 3 by 2 means half and gamma half. So this is equal to 1. So 4 pi a cube into 2 and 2 4, it will cancel. So 1 by 4 and gamma half equal to root over of pi. Root over of pi and b cube equal to b3 by 2 equal to 1. b3 by 2 equal to 1. So 4 cancels, and so a cube and here pi and root over pi means pi by b 3 by 2 equal to 1. So actually so this a equal to b by pi to the power half, b by pi to the power half. So this is the value of a. So expressions of a in terms of b, we could write here a equal to b by pi to the power half. If we put here, then dnc by n equal to 4 pi and b by pi to the power 3 by 2 and e to the power minus bc square and c square dc. Now it is our only one task to find the value of b, and for getting this value of b, we shall have to borrow one data. We shall have to borrow one data from this kinetic theory of gas, and this one is c square bar, mean square speed. It is called mean square speed, and this is equal to root over this is equal to 3 by 3 kt by m, 3 kt by m, 3 kt by m, 3 kt by m. This data we have to borrow from this kinetic theory of gas. Now we shall also get the mean square speed value from this distribution law. Distribution law has been popularly used to find this average or mean value of this property. So actually c square bar equal to integration 0 to infinity and here c square and dnc by n. So you can write here this value 4 pi you can bring it outside of the integration, b by pi to the power 3 by 2 integration 0 to infinity c to the power 4 e to the power minus bc square and bc. And this again, this integration again has to be done easily by use of gamma function. Here n equal to 4. So this is equal to 4 pi into b by pi 3 by 2 into gamma 5 by 2 and twice b to the power 5 by 2. And this value actually 5 by 2 gamma 5 by 2 equal to 3 by 2 into half into root over 5 means 3 by 4 root over 5. So total value C's mean square speed is equal to 4 pi and b by pi to the power 3 by 2 and this one 3 by 4 and here 2 3 by 8 into root over of pi and divided by b to the power 5 by 2 and the value comes up. This value comes up 4, 2 and 8, 2 and pi to the power half and pi to the power 3 by 2 cancels and b 3 by 2, here b 5 by 2, so this is equal to 3 by 2 and 1 by b and this value is equal to 3 kT by m. So 3 cancels, so b by 1 by 2b is equal to kT by m or b equal to m by 2 kT. So A now becomes B, putting the value of B, then m by 2 pi kT and to the power half. So the total expressions of the Maxwell distribution law, this dnc by n equal to 4 pi and instead of kq we can write m by 2 pi kt to the power 3 by 2 and instead of b we can write m and c square by twice kt and c square dc. So this is the derivation, full derivations of this Maxwell distribution law. We can also write in another way. Again I tell you, this is the fraction of the molecules having the speed c to c plus dc or probability of a molecule to have the speed c to c plus dc. This could also be written as dnc by n equal to 4 pi and here m multiplying by Avogadro number, molar mass into multiplying by the Avogadro number, it is equal to molar mass and divided by twice pi and k also multiplied, then it is RT and to the power 3 by 2 into e to the power minus, again in this case also mc square by twice RT and c square dc. So actually this fraction or probability of a molecule to have the speed c to c plus dc depends on the molar mass and the temperature, or more precisely we can write it depends on m by t. So actually the same fraction of molecules having this speed, say for oxygen at 300 Kelvin is same as sulfur dioxide at 600 Kelvin, as m here oxygen at 300 Kelvin is same, this to dnc by n is same, here also same. Here m is the 32, here m is the 64, so here 300, it is 600. M by T will be the same in both the cases. So these two gases at two different temperatures have the same distribution function or same distribution curve. Or you can say dNc for same is same for a nitrogen gas and carbon monoxide gas at any temperature. At any temperature, both are having the same molar mass. It is also 28, here also 28. So carbon monoxide and nitrogen both are having the same fraction of the molecules, are having the speed C2, C plus Dc at all temperatures. I now give you one problem to calculate, whether you could calculate or not. Calculate the percent of oxygen molecules at 300 Kelvin and that have speed 500 meter per second to 510 meter per second. In this case, M you can put here this M equal to, you can put M equal to 32 into 10 to the power minus 3 kg per mole in molar unit, T equal to 300 Kelvin, and C equal to 500 meter, and DC equal to 10 meter per second, and DC equal to 10 meter per second, and R, of course you write this 8.31 joule mole inverse Kelvin inverse. So this can be given as the homework, and in my next class I will show what will be the answer of this problem using this formula. This is all about today's lecture of formulation of Maxwell's distribution law, and in my next class I shall discuss the salient features of the distribution curve and variety aspects of the distribution curve in my next class. So thank you all who are watching this video.